I mean, so we're going to start with exercises, so you don't need to actually look at this at the beginning. So you can go on this side basically at the start. We'll do 20 minutes of exercises. We'll talk for about 30 to 40 minutes, and then we'll do the rest exercises. Okay. Right. So exercises for the first 20 minutes. Go on the repo exercises.md. Hopefully there's not too many typos in the instructions that tell you how to get set up. And then it will lead you into questions. So we'll start with unit test questions, and then we'll, basically get as far as you can with the unit test questions. We'll do the other questions afterwards. And Isaac and I can basically be here to help you. Right, so what we'll do is we'll jump back into teaching some stuff for a bit. So Isaac's going to continue on for us and talk about integration tests. I'll talk about property tests, and then we'll go back to doing exercises. So I think that's over to Isaac probably. Do we have to work with the sound microphone? I guess it should be recording.
Yeah.
Let me go. You may start, and I'll take this.
All right, so now we're gonna be looking at integration tests, what they are, and then we're going to have a brief look into end-to-end tests. So first, understand what integration tests are. You need to understand what a component is. Think of a component as a self-contained slice of logic. And the component can also integration testing is when you test two or more components or modules working together. And the difference between unit tests and integration tests is that integration tests focus on the connections between the components, or the connections between the functions, rather than the logic within the function. So it doesn't test the isolated logic, but tests the connections and how the components work together. So we can think of an example where you have three different functions, A, B, and C, and you want to test them all working together. So we can define some example functions, -1, add 1, and double. And then if we want to integrate it, can do some very complex maths, and we can change these functions by passing x into -1, and then the output of -1 will pass to the add1 function, and the output of the add1 function will be passed to the double function. And this type of function can be called a driver function. So the driver function can connect two or more components or two or more functions together. So now that we have the driver function over here, you should have seen parameterizations in the previous session. We can now pass it. We can now pass this driver function some input data. So we have we label the inputs given and expected. So we give it input of 5 and we expect an output of 10, and then we can pass these inputs to the function, and then the calculate driver function will do the computation, and then it'll check if the output of the driver function is equal to the expected value. And that's testing the combination of the three function values earlier. So this is a very trivial case of integration testing. So now we can think about stubbing dependencies. So stubbing is essentially just replacing replacing some functionality with with a constant output. So the benefits of this is that it can speed up tests. So if you have a function which does a very complex computation and it takes a lot of CPU hours, you could just say, instead of doing all those computations, I would just return a single value, which will kind of mimic the behavior. So, and it also allows you to isolate behavior, because if you get a constant value from a function, you don't need to think about whether that function is correct. You can just test. You can have a component A and a component B, and if the component B outputs a constant value, then you can only focus on testing whether A works without worrying about whether the implementation of B is correct or not. So that's another advantage. So this is example function of calculating temperature change. Hopefully it's correct. I don't know, I'm a computer scientist. So this is just a function to calculate the temperature change. And now we can create a stub function of this. So this, to explain this, it takes some value heat flux and depth and the initial temperature, and then it calculates the temperature change, and then outputs the temperature in degrees, the new temperature in degrees. So you can just stub this instead of doing all that computation. You can just say return 5 degrees, and then that reduces the computation. And if there was any bugs in this, it will you just have a constant value, so you don't worry. So now we're going to be looking at two methods of integration. So one is top-down testing. So with top-down testing, you start with high-level components first, and then you incrementally add new layers of functions. So you can think of having a top function which holds two functions, and then those two functions each for two functions. So you can think of it like a tree. And we'll look at an image of this shortly. But top-down testing is good for validating raw behavior of your function or your software. So making sure that's generally doing the right thing. So this is example, maybe you're doing online shopping, buying another thing that you don't need. And you might, so this is a checkout function. So you might think of the different things that need to go into the checkout function. So I'll do that. So if you want to check out something, you put things in your basket, and then you click on checkout. First of all, you need to calculate the price, because nothing in life is free. So you might need to calculate the tax and calculate the discount. And then you also need to pay for it. So you also have a process payment function. And then with top-down testing, you would stub. So that means you would replace all these functions with just a defined return without doing all the computation. So you can stub all of these calculate tax, calculate discount, PayPal gateway and card gateway functions, and just make it return a single value. So for example, you could return a constant 20% for calculate tax, and return maybe a constant 5% for discount, and then PayPal gateway or card gateway could just return, like a success or true boolean to make sure that the payment has been processed correctly. So that'll be an example of using top-down testing and stubbing the lower level functions. And then you'll just be testing the logic of the checkout and the calculate price and the process payment. And if you're doing the checkout, you'd probably want to make sure that checkout does the broad behavior they're expecting. So once you've checked out, it sends your order to the warehouse to be processed. So you're testing the top layers first, and you're stubbing the lower layers, and that's the gist of top-down testing. So bottom-up testing is, I've guessed it, is opposite. So you start with the lowest level components first, and then you build up testing each new layer, and you test you implement the bottom functions, and then you combine them together and test it, and then you so you can imagine doing the calculate tax and calculate this stuff integration first, and then do the PayPal gateway and the Cardway gateway integration first in the first payment, and then gradually integrating the calculate price and process payment functions and integrating it up. So you'll start from the bottom and you're testing the integration stuff and go up. So bottom-up testing is helpful when you have lower level code, which is more complex, or you are doing a refactor. So in the ICCS, we actually have the project where we were translating MATLAB to Python, a very long project.
I mentioned it in the first session,
Okay.
actually, it kind of came to my mind when I was talking.
Me, Dominic, and a few others worked on this project. And bottom-up testing is good for being able to localize where your errors are early in the code, because with top-down, with bottom-up testing, you can ensure that essentially your bottom components work very well. So you have tests at the lowest level. So any error that you find that you see straight away, you can immediately catch where it's at the lower level. And then as you integrate more, you can, since you know the bottom levels are correct, you can then say, since the bottom level is correct, and I've added a new layer, and the new error is most likely to be in that new layer that you added. Because the previous layer that you tested you have some confidence. Dominic, when we spoke about verification at the start, testing is not proof that your code is correct, but it gives you some. Bottom up, and go to the top. So if you want to choose an approach between top-down testing and bottom-up testing, it's important that you're not dogmatic, saying the top-down is best or bottom-up is best. You need to choose a style that suits your code base. And typically, you don't just choose one or the other in your code base. You're going to be mixing and matching depending on what works best. So we've been talking about integration testing and how they test the logic between components rather than the logic within components. So with integration testing, you're testing the interfaces. So, and the common issues that you might have with integration testing is like mismatches in the interfaces. So you might have a function that outputs kilometers, and then you might create a function that is expecting meters. So you would have like so your values will be off by a factor of 1,000 if you try to integrate that and you made a mistake. And it's the same type of logic you can apply to time steps, daily versus hourly, or percentage versus decimals. So you could have 50% versus 0.5. And it's important to handle things like nans. So you might have a function that's not expecting nans. So you need to be able to handle that in some way. And maybe wrong data types to another. You might output a list, and then you might pass it to a function that is expecting a NumPy array. And memory can generally affect. It can affect all code, both communities. So we can see an example of a very expensive state. So we have a Mars rover. You might have heard about this during your A levels. I certainly did. It was a project by NASA collaborating with some other people I can't remember, and they launched this expensive Mars rover in space. And after 10 months of traveling, it burned up in orbit. And it led to a loss of 125 million, and years of people's life work. So you can argue that testing saves years of your life. So this was caused by a mismatch between the units that were used to calculate the acceleration. And that's as much as that. So yeah, they had a mismatch in units, so the calculation for the acceleration was wrong, and it led to the burnout of the orbiter and a loss of 125 million volts at that flat. So you might ask yourself, what should I prioritize when I'm doing integration testing? So you might want to prioritize high risk interfaces, but
Not now.
you might want to prioritize high risk interfaces. So this Mars rover is a good example of a high risk interface. You probably, in this case, you probably would have wanted to do some bottom up testing of the components, not top down, where top down would have wouldn't have worked as well. So bottom up to make sure that these expensive components are working properly before they're integrated with the rest of the rover. You're gonna prioritize complex combinations of components. So you have complex combinations, it's easier to make mistakes when you're doing more complex integrations, and components which integrate components that you plan to change. So you might have a function A and it called a function B. You might change that, or you might change that function B. So you'd want to ideally test that. So now a quick overview of end-to-end testing. So end-to-end testing is when you run the entire system from start to finish. This could be, for example, running a climate model or ocean model, initializing parameters, and then running it for like 100 years or something. And typically, this covers the main flows of the program. And you might think, what's the difference between doing a bottom-up integration test or a top-down integration test and end-to-end testing? So in the example, we saw the checkout. We saw top-down testing on the checkout. So if you're doing like an end-to-end test, that would include, going to the website, adding stuff to the basket, and so include the whole process. So that's just an image of the different cases that you can come across in end-to-end testing. So if you imagine a climate model, you could run an end-to-end test for like 1 degree resolution, or you could run an ocean model at like 1/4 degree resolution. And the pros of end-to-end testing is that it confirms that everything works together, but it is very slow compared to integration and unit tests, and it's very hard to localize bugs. And typically we have this diagram. There's been other diagrams, but this diagram is like widely accepted, that you have a large number of unit tests because they're easier to write. Then you have fewer integration tests, and then even less end-to-end tests because they're slower and less fast. So as you go up, it gets more expensive to run these tests, and you have fewer of them. So in summary, for integration testing, you should integrate early, test often, and start when appropriate. So when you might have some complex functionality, and choose a top-down or bottom-up approach, or in most cases it will be a hybrid approach when you're deciding on testing. And keep an eye on interfaces. You don't want to lose 125 million.
Great, thanks, Isaac. Yeah, so with the integration testing, you can kind of use all of the framework that we've had so far to do that. So you can use PyTest. It's really just about the architecture as Isaac has explained. So I'm going to talk about the last part, which is property-based tests. I kind of teased this at the end of the first session, but I'll go through what I said again. So a question you might have, and we kind of touched on this a little bit, is like, does integration testing and unit testing scale? Like how, if we're doing something like this, but we haven't covered the entire input space, or we have like lots of complex behavior and a big code base that we want to test, can we really kind of use this technique to get a good understanding of the correctness of the software and verify it? So that's just a quite small input subset of the input space, but it was like a really simple function anyway, so maybe that's fine. But thinking of all of these corner cases is hard, and the more complex your software gets, the harder it is to think of all those cases. If you think you're actually building some serious model, it takes lots of time to write all of those cases and find them all, and maybe you won't think of them all as well. So you might then think, well, can we automate this in some way? So this is what property-based testing allows us to do. So the idea with property-based testing is, rather than us thinking of lots of specific examples, we should think much more generally about how our program should behave and have the computer do the hard work for us. A general lesson that you learn during a computer science degree, which I did, is like, you should be as lazy as possible. Like, being a computer scientist is about being lazy, about doing as little work as possible, making the computer do things for you. So I had this example before, I'll go through it again. Let's imagine you're making a library that's just like basic data structures, and you're working with lists or strings, and you write a function to reverse a string. You probably wouldn't do this in real life because this is already in some library for you, but it's a good example. So there's a property you might think of for your function, reverse function, that like reversing a list and then reversing it again should give you back the original output. So you could go and write a bunch of tests for this that says, okay, start with the empty list, we do it systematically, have a list with one thing in, okay, the reverse doesn't do anything, okay, maybe a list with two numbers, 1 and 2, okay, reversing it 2, 1, back to 1, 2, you could do all of that. In property-based tests, the idea is to actually keep this property general and have the computer generate lots of inputs for us automatically. So we'll have another bit of software called a generator, which, based on this type here, which I've said is a string, it's like a list of characters, it will systematically go through all of these possible cases for us. It will generate some random inputs as well, and this way it can find counterexamples. So this technique was invented in the programming language Haskell. The library there is called QuickCheck. That's where it came from. It's about 20 years old at this point. Lots of other languages have some kind of variant of QuickCheck that's being re-implemented for them. Python has Hypothesis, which we'll use, which doesn't provide everything that QuickCheck does, but it's pretty good. It gives you quite a lot. So that's what we'll use today. So the idea is, like, you as a programmer, like someone who's testing it, you write this property function and predicate, takes in something of type A and produces a Boolean result. And what the framework provides you is this generator, actually in PyTest and Hypothesis, it's called a strategy. That's going to generate lots of A's for you. And the idea is the framework is going to take this and run it lots and lots of times. Typically, the default is 100. So rather than you having to think of 100 inputs, you just write this and it does it automatically for you. So that's great. And if this fails, it goes through a process called shrinking, where it will actually try and simplify that example to get the smallest failing version. So rather than sort of giving you something really complex and saying, well, it failed for this, it will also do this shrinking step, where it will say, okay, it failed on this. Can I simplify that example and find something else that failed that was smaller? So that all happens automatically for us. And what it will spit out is, here's a bunch of counterexamples to this function. Here's some things that it fails on. So we're going to do that. We're going to use Hypothesis. It builds on PyTest, and strategies are these generators. So we can import the Hypothesis library, and we get this macro called given. And I'm going to use some strategies here called floats and lists. So what we're doing here is specifying some generator. We're going to write a test. I call it prop here. It takes some input data, and that's going to be provided by this generator, which I've specified with the given. So going back to this like diagrammatic form from before, this @given lists floats is saying, I want a generator for lists whose elements are floats. So what that's going to do is generate 100 floating point lists for us, and it's going to call this function with every single one and sees what happens. So I'm going to do some demoing on this. Where does this slide go? Okay, so we automatically generate 100 inputs, and we can. Lots of the interesting stuff comes about with actually trying to refine these strategies. So I'm going to start with an example. Sorry, Nico, I'm going to go over here and be in the corner typing. And I'm going to take this file and delete all this and start again, which is going to be interesting. So let's think about a general property that might hold. Okay, what I should say is, let's say I'm taking this energy balance model and I want to compare it with observation. So I start building some library to deal with observational data, and I want to do some tests. So I make a mean squared error function. And in these examples, I'm going to test the behavior of mean squared error. Now, I do a little bit of thinking about maybe we do it in a test-driven development way. I don't know. But for the purposes, I've already written it. We might think about mean squared error and how it behaves and think, okay, it produces a float, but it should always be positive, right? Because it's the mean squared error. So we're never going to get a negative number. So that is a general property that should always hold no matter what I do. So I'm going to specify a generator. I want to take floating point lists. Oh no, this is the next example. I'm going to do this where I say it's always positive. I can think of something more simple first, which is to do mean squared error on the same input. So mean squared error, you're comparing like an observational data to model data, and it's computing the error. But if I give it the same 2 bits of data, then the error should be 0, right? The error between a piece of data and itself is always 0. So essentially there's no error on the same data. So I can codify this as a test that says mean squared error on input data is equal to 0. And what I've done here then is specify this generator, this strategy, which is going to run this function loads of times. So let me make it bigger. Is that sort of visible? Yeah. Let's see what happens. Oh, sorry, I didn't give it to itself twice. Good. Let's see what happens. Well, it failed. Okay. Good. So let's see why it failed. Infinite data with the infinite representation, which when we pass that in is actually producing a nan, and nan is not equal to 0. So that's something I didn't think about in my code. What do I do with the floating point infinite representation? That sort of makes things weird. So I might now go back and change my mean squared error function to deal with that. In this case, I'm going to say, no, I don't care about that particular kind of input. What I'm going to do is I'm going to change my generator. And with generators, you can parameterize them to kind of refine down the set of things that are being generated. So I can say with floats, I don't want to allow infinity, and I don't want to allow nan. So maybe I'm saying, I don't care about those. I don't care what happens with those particular inputs. So in this case, I'm going to change my generator. So I'm going to make this refinement here. And run it. And now, great, that passes. So, you might have gone and changed the function. In this case, I'm just going to keep my generator. So for all of the stuff it tried, that was okay. Okay, now I want to go back to this idea that it should always be greater than 0. So for that, I need 2 lists. I want to take any 2 lists and say, no matter what I pass in, I always get something that's greater than 0. But I have to be a little bit careful here because I need to have lists of the same length. If I start off doing this, let me start it and start making this thing here. I can just do pair of these things like that. And let's say all test mean squared error always positive, and I'm going to get model data and observation data, and I want to assert that mean squared error of model data and observation data is greater than or equal to 0. Okay, so I'm going to run this, and it's going to fail because I make typos. Okay, it's going to fail because one of the things it generated for me was empty list and a list with 0 in it. It's saying this is a counterexample, and it fails because my code throws an error and says, well, I can't do mean squared error if the things are the wrong size. So model length and observation length should match. So I go, okay, that's fine. Maybe I codify that in a test. But for this particular thing, I want to only generate model data and observational data of the same size. So I need to make a custom generator. So we can do that with a special decorator called composite, which lets us define our own generator out of other generators. So I write composite like this. This is going to let us build a strategy, and we then write a function that takes this argument called draw. Draw is a function that we can use to dynamically pull out a value from another generator. So what I'm going to do is use the lists float generator and draw out a value from that, get a first list. I'm going to do it again to make another list, but one of the things I can do to refine the list generator is to specify its size. So in this case, I'm going to say the minimum size and the maximum size of the second list needs to be the same as the first thing that I generated. So it's going to generate me a list using draw. I'm going to generate another one, but say that one has to be the same size as the first. So this is a little bit of extra keyword arguments that belong to this list generator. And then I return the pair. And then I can feed this as a generator now into my function. So let's do that. I'm going to do the Blue Peter thing. Maybe I thought I saved the previous. No, I deleted these shots. Yeah, no, it's okay. I can just write it quickly. We can see me again. Sorry. So we get composite. We want same length. Float list. We're going to draw. We want list one. We're going to draw from lists with floats in. And actually, we're in a situation where maybe we want to do this thing where I'll do it in a moment, actually. So floats like this. We're going to get list two. We're going to draw from that with floats. We're going to say the min length is the length of the first thing. We're going to say the max length is the length of the first. Like that. And then we can return the tab. So I'm going to replace this generator.
Should be list one.
Just one.
Thank you.
And should be list on the line above.
Brilliant. This is great. And you sit in my office all the time. So now I'm going to give that generator. I don't have this argument anymore. This gets like filled in by the this is actually going to give me a single input that I then need to pattern match on, which is a problem. I can just take that. So now I'm in a position to use my custom generator. It's going to give me things of the same length. Let's see what happens. Oh, it's not called length, sorry, it's called size. We run it and we fail. We found two failures. So we got something that was very, very large given to us. Okay, now we have two lists of the same size, but this had a very large input to it. And we didn't handle that. We get some like numerical overflow here. So maybe we have to go back and think about how we handle that in our function. Well, what if someone gives me a really, really large value? Maybe I want to not allow that. Okay, in this case, I'm going to do the other thing where I change my generator. I'm going to say that, okay, this has a max value of this and maybe a minimum value like this. So maybe I'm saying, I don't care. I know that I'm never going to use this on very good values, perhaps based on how I'm using it, domain. Okay, and this passes. So I've tried this on 100 different list float inputs that then are of the same size, values in this range, and everything's okay. Okay, so the kind of general paradigm we've got here is to have some diverse inputs. Those are generated for us, so we don't have to think about that. Combined with some strong properties about our programs, and this gives us stronger tests than just standard unit testing. But the difficult thing is, how do we create these strong properties? How do we come up with good properties? I did a little bit of thinking like, oh, the mean squared error should always be greater than 0. It should be 0 if it's the same data, but there's lots of functions that have that behavior. It doesn't really characterize mean squared error very well, does it? So we need to think a bit more. So there's a really neat paper called A Guide to Writing Properties of Pure Functions, sorry, How to Specify It, A Guide to Writing Properties of Pure Functions, by the guy who invented QuickCheck. And he sort of says, okay, how do we actually come up with good properties? He observed after sort of a decade plus of using this in industry, that people start writing property-based tests that kind of reproduce the original function in the test. They kind of replicate the code like, oh yeah, let's call this function and its behavior should be this, and you kind of end up rewriting the function in the test. And it's not very useful because probably you'll just do the same thing or do it wrong in the same way. So he has a bunch of general ideas, and I've kind of tweaked these myself for this particular area. So one is called the post conditions idea. And that's to look at the relationship between the return values, things that you get produced, and the original arguments. Like what is true after you've called this? So the idea of going back to like the reverse function, you might want to look at the fact that if you reverse a list, all of the stuff in the list that you've reversed should have been in the original list. They shouldn't be creating new values. And vice versa, everything that's in the input list should also be in the output list, just in a different order. And you could say that for things like sorting functions as well. So that's like a relationship between something about the output and something about the input in both ways. So that can be very helpful. Think about how those inputs and outputs relate in a general sense, but that's always not necessarily sufficient to characterize everything exactly. Another is about validity testing. So like what's the kind of space of valid outputs? And I think this example with the mean squared error saying like everything should be greater than 0, that's a kind of validity test. It's like, what are the set of valid outputs for mean squared error? But it really shouldn't be negative. So we try on all like a whole bunch of possible inputs and see, does it always have a particular does it produce valid results? Does it always produce something that's greater than or equal to 0? Could someone click start my video on that?
Okay.
Okay, don't. Right under. This is the owl trying to like reboot itself. Okay, it's come back. So we can define some kind of validity. This is one of my favorite ones, to think algebraically about our functions. So go back to our like sort of mathematical training. If you've done these sort of abstract algebra or group theory or things like this, you might start thinking about like, how does this thing behave in terms of general properties? Does it have an inverse? You might think about that. So like the square function has an inverse. So you could say for all inputs x, square of x times by 1 divided 1 over x to the power of -2 should be equal to the original x. So like if you invert the operation, you should get something back. Or maybe it's self-inverse, like an involution. Is it commutative? Does it matter which way around the arguments go? For mean squared error, it doesn't matter, right? You can flip them round, and so it should be commutative. Is it associative if you need to do like combine 3 things together? How do you group them together? Unitality, is there some kind of input that, well, like, so unitality is like for plus, the unit value is 0. So 0 plus x is x, or for multiplication, 1 times x is 1. So is there some particular element that when you combine it with something else gives you back the other argument? So this is a good way of thinking of other properties that should be there. So I might codify this for mean squared error. I won't bother doing the symmetry one. Perhaps I'll leave that as an exercise in the interest of time. Okay, last one, metamorphic properties. So this is to do with making several calls of the function that are somehow related. Maybe there's like a slight difference between them, and then seeing whether the results are also related in some way. So related calls return related results. So this is where we start getting into sort of more interesting scientific ideas. So you might look at properties that relate to symmetries or like invariance. So is there some invariance in your function? Is it invariant under scaling or rotation or something like this? Can we think of other properties like conservation, which maybe is slightly more of a post-condition check? Like, is mass or energy conserved by this particular part of the model or something like this? You know, no matter what the inputs, we should always have some kind of conservation properties. So this starts to become really interesting in the scientific context when we're bringing in the sort of science, like the kind of physical behavior, and codifying those into tests and saying no matter what the inputs, it should behave in this physical way. So for mean squared error has a kind of scaling behavior. There's a kind of invariance property about scaling. If we scale all of the inputs, then it's going to scale, let's say we scale all of the inputs by a factor s. So we scale the model data and the observation data. Then that's going to scale the mean squared error by s squared, if we've implemented mean squared error properly. So this is a kind of an example of an invariance. It relates to sort of Noether's law. It's about how we kind of, if we scale all of the inputs, there's a kind of scaling that we can do for the output that then connects the two together. So I'll write that very quickly. We can reuse our previous generator to get same length, two lists of the same length. I'm also going to generate floating point number, which I'll do in the same way as this, which is going to be my scaling factor s. So I'm going to get my input data. I'm going to get my scale. And I'm going to do something similar to what I did before, like this, split my model data out. Now, what I'm going to do is start by running the scaled version. So I'm going to make some scaled version of my data. So I can do scale times model data, input data, scale times input data. And then I'm going to calculate the sort of scaled mean squared error. So sort of mean squared error for scale, let me call it that. So that. Now, if I do the original mean squared error and then scale it by the scale squared, so do it on the original data, then I want to assert that these two things are equal. Sensing some floating point things are going to hit me, but let's see what happens. So I've got these two calculations. The MSE of the scale data, and then this sort of scaled mean squared error here. And those two things should be equal as a kind of invariance law.
Multiplying this.
They need to be numpy arrays, don't they? Let's see, it might be doing this for me. Let's see. Yes. Right, so I should make these into numpy arrays, which so then I can get that nice lifting for me. Let's see.
need to do observation data.
And then you scale the input data.
Oh, sorry, yeah, that's what am I doing? What am I doing? Thank you. Okay, so we almost succeeded, but we had a bit of floating point issue. So that's okay. I'm going to use the NumPy is close this time around. We saw a prox earlier this morning. Okay, there we go. So we've got this nice property about the kind of physical behavior, well, the mathematical behavior in this case, this kind of invariance property that we've codified, and that's quite a strong property. There's not a lot of functions that are going to behave in this way. So we have to work quite hard to make something that's not mean squared error that passes this test. So that's the kind of general idea. So property-based testing is a I think a super powerful technique. It's really not very well known outside of computer science. You can combine it with other approaches. So combining property-based tests with unit tests, I think is sort of is like the real maximal power, not just doing one, but doing both. A lot of the cool, interesting work comes into custom generators and shrinkers, but that's something to talk about another day. And yeah, there are frameworks in many languages. I think there's like 50 languages that have this kind of property-based testing framework. There's a neat paper that someone wrote recently trying to think about how to apply this to ocean models. So Deepak Cherian, I can't remember where they are now, but we had a bit of a chat after this. He's been thinking about how you apply this idea in a kind of full-on modeling context. I think he's sort of started doing this as a kind of ideas paper about how to do it. So if you're interested in that, take a look. Okay, great, thank you. So I went a bit over there, but we can go back into our exercises now. There are exercises about property-based tests. You could jump over the remaining unit test ones if you want, or you could just keep going with the previous ones. I'll leave it up to you. Happy to help with either. Yeah, sorry,
I have an incredibly nerdy point about testing whether things are close using NumPy is close.
Oh yeah.
Which is that in NumPy it does this really neat thing of broadcasting, that it checks if the dimensions are compatible. If you've got like one array has only got one is missing an axis, then it checks if things are broadcastable. And NP is close broadcast stuff. So if your arrays are different shapes, it will see if they're compatible and then check if they're close once it's broadcasted them. But they might be different shapes. That might be fine. That might be what you want, but it does do it. And there is another thing called in the NumPy testing module, there's an assert is close or assert all close, which doesn't do that.
Yeah.
So the two subtle, there are all sorts of subtle differences about the testing thing that you just, and I've been bitten by that particularly.
Yeah.
It's like, oh, they should be the same.
Yeah.
So there's all sorts of intricacies.
Yeah, I feel like I tend to use NumPy all close.
Yeah,
When I'm working with arrays of things. Yeah.
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 So it's just that I'm recently bleeding from that particular.
So yeah, test your tests.
Yes.
Nothing like, you know, are your tests hiding something you didn't realize? Is interesting.
in that case, you're testing against the
When you're
Boolean.
so failing first,
You just
because I
realize,
can consideration
Boolean is specified in
was broken. She wrote a test. It passed. The test passed, but the test was just not picked up.
Yeah.
So,
Yeah.
So you can
Yes.
just write it failing first, just to make sure that the test is actually running.
Yeah, the classic one is doing this. Being like,
Yes.
yes, my test passed, but you forgot the assert, so it was never actually run. You could say, you know, like this, and you're like, ah, brilliant, my code's all correct, right? But you never actually run it. I've done this. Yeah, okay. Yeah, so this is a little bonus extra for people who you might look at it later. At the end of the exercises, we describe something called doc tests, which are comments that contain tests inside them. So you can write a function with the comments and say like, oh, yeah, have an example in the comment that like, oh, this function should behave like this. And that can be run as a test as well, by the way. So we didn't have time to cover it today, but there's an example in the code base. The last section of the exercises is kind of pointing you at that.
The other place that's really useful is if you're documenting your functions, so you're writing a description of your function, it's going to be turned into HTML. You're writing that kind of documentation. If you put an example in there, then you can check that when it gets run, it's actually giving you the right answer and it's
Yeah.
not outdated. So it keeps your
Yeah.
documentation up to date as
Yeah.
well. So doc tests,
Yeah.
super useful.
Yeah, they stop your examples getting stale.
Drifting.
Yeah, I've definitely done it. I've written an example in a comment and then later on it's just been not true in. So it makes sure that your comments is from machine checked as well. So this first question, looking at the energy out function, which is about the kind of energy that's reflected back out of space, determines the energy radiated from Earth or the planet as a function of its temperature, assuming it's a black body emitter. What's a property that we can always expect of the output? And we should write a test for that. So this is like a validity kind of property. So it's producing energy. So I think we should expect that, and this is a temperature in Kelvin, so this should be not negative. So one thing we could expect is that the output should always be greater than or equal to 0. It should always be outputting energy. It will always have a positive energy. So this is a bit like that test where we say, well, mean squared error should always be greater than or equal to 0. Okay, different kind of scientific domain, as it were, but now we're thinking about, okay, this, whatever the inputs are, as long as those things are greater than 0, the output should be greater than 0. I think there's a stub that we put in the there's a stub that we put in the test energy balance for this. Unfortunately, we should put a stub for the other exercises because I think that this got reused by some of you for exercise 1. But we can comment that. Start thinking about how we test this. So it's a function of temperature, and that'll be there. So we want to put the temperature in, say it's always greater than 0. So now we need to generate those temperatures. So the middle value is 0. Okay, if we put in something very big, it's not happy. So I'm going to put a max value in this. I was doing it to the power 4, so let me put that a little bit lower. I hope the Earth's temperature doesn't go to 1 times 10 to the 20 in Kelvin. But yeah, so that gives you question 1. And notice that I called the init function explicitly here. You have to mess around a bit to do fixtures with hypothesis. It is possible. I forgot how to do it. We have done it. I remember we did it before, but I couldn't remember how to do it. And I couldn't quickly work it out, so I just explicitly called init here.
Is that this hypothesis sort of takes over the name of the input?
Yeah,
Okay.
but it is definitely possible.
Yeah.
I thought you could just do it like this, but
That makes sense, wouldn't it?
You think you need to specify like a special generator?
yeah, you have to
That's argument, like
specify
there is
some
like a magic
components.
syntax, which is somewhere in the docs. It's like,
Yeah, that's
You
confusing.
might want to change the scope of your fixture as well.
Maybe that's to do with that. So
I
I thought it
did
was
model.
this, but then I got this complaint.
Scopes.
Yeah,
Yeah.
function scope fixture,
Yeah.
blah, 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 blah.
yeah,
If your picture is module scope feature.
Different function scope fixtures, yeah. We did it in something, and I was looking at before I couldn't looking what it was, but I thought it's not actually that relevant, but let's spec out to this. I don't know actually.
it's just,
But it seems an obvious common feature that the context still uses hypothesis and things.
Yeah.
It seems like a common yes. So make it hard to do.
Yeah. We definitely worked it out because we have a project where we did this and they're really complicated fixtures, like super complicated. So we needed it because otherwise we'd be paying. But we did work it out. Couldn't easily. wasn't obvious, but.
Mm.
So the next question is looking at this linspace function from before, which is already defined. It's just a helper. It's, you know, it's something that is in NumPy already. You can see that it. There's some helpers. It's the classic. You want to generate a bunch of. Generate a. Let's do linspace. Ooh. Oh, no, let's do a number there. So it's like, okay, I want 4 numbers between 0 and 10, so evenly space them out kind of thing. So, okay, let's think about some properties based tests for that. Not unit tests, but property based tests. So the question here is to write some post-condition style ones that relate values in the output to things in the input. So we can already see from this example what values in the output appear in the inputs.
The first and last.
Yes, the first and the last, the start point and the end point. They're there in the output. So we should always have that whatever we put in here should be in the first and last positions, no matter what the data is. Right, so we can start making that into a test. And so I think we've got the start. Oh, this. Prop. No, it's not that. Okay, that's fine. We just start doing it here. So we need test helpers param. Okay, there's a stub in test helpers param. That's where it was. So we want some floats, 2 floats, one integer, which we need to import. So if I do this linspace first, get the kind of space out. Oops. And then I can assert that space at position 0 should be equal to the starter, and space of what's this? Like this in Python. It's like that. Imagine I could get some size issues. Oh, I was thinking. Yes, this might be. It's generating a very large number of inputs here. Because it's going to generate 100 times 100 times 100 inputs here for these 3 things. So that's probably why it's taking a long time. So what we can do is actually do a tuple like this. Tuples. I think it's tuples. I think they're all written like this. Tuples. Yeah. So that will just generate 100 of those. So I forgot to explain that before. So this failed because we didn't think about this. The fact that if the count is 0, we get an empty list. So that's fine. I'm just going to do this. And always make sure I have at least one thing. Like solution to this. I think it's taking too long, but just generate.
Yes,
Could you make the end just related to the start?
Yeah, great idea. See what it failed on. 0. I've got 0. 0.
I think it needs to be at least close to it. So this is close to the thing, to end.
Yeah, okay, so we should probably put some, we could put some connection in.
Actually, it's a good example, that when you write those things, it actually makes you think about the function.
Yeah,
And like exposes you to all edge cases that you kind of forget when you write them. I think now it's just generated like something into the.
yeah, okay, yeah,
so it-
that could have been the issue, sorry, so Max. Um. Yeah, that's probably what's going on actually, isn't it? Okay, so we're not like that.
So you need the count to be positive as well.
Yeah, thank you. This is brilliant. I'm loving this crowd problem solving. And infinity hit us again. That's fine. So we should allow. Maybe I'm gonna preemptively put this as well.
It's like a live demonstration of pair programming, but
Yes.
with just more than two people.
It's basically how I teach my undergraduates, yeah. I do stuff until we make it work. There we go, so that was good. So that's an interesting that we have to think about count. I guess we could have just put now that I'm thinking about it. So we've got, yeah, so that's good. So that's one property we could think of. Yeah. Great, so I think we better stop there and get some lunch. I wasn't expecting us to get through all of the exercises, so they're there for you to kind of try later and, you know, whether that's today or on the journey home or another day. And if you spot anything that's broken or wrong, you can make an issue or PR on the repo, that would be helpful. Yeah, happy testing. I hope that's been useful. Do keep testing. Yeah. Wrong.